We're going to move on now from CalFed. There's a couple, but we're going to move on and we're going to do statistical thermodynamics for 3 or 4 lectures. So all right, so a note on the reading here, almost everything that we're going to cover is going to be in chapter 6. In the syllabus, I also have assigned chapter 3 of a different book by Chandler, and that PDF is on the website. That is a more advanced book. You don't really need the formalism in that book to do the problem sets, for instance, or to succeed on exam 3. So I would say that reading is a quasi optional. I hesitate to say that because I wonder whether anyone will read it at all. But it helps to know that because it is a more advanced book. I find that presentation in Chandler to be just masterful. I really like that book. I like how it's written. I like how the material is presented. I like how it's presented better than the way DeHoff presents this topic. But that said, it is a little bit more advanced than we need. Right, so it's good that you know that. So let's talk about microstates, macrostates, and microstates. Macrostates and microstates. So let's start with microstates. A microstate, this is key sort of foundational definitions. This is a description of the state of every atom in a system. Every atom in a system. So that's kind of crazy, right? That's a crazy thing to think about, is describing every atom in a system. In practice, we almost never do it, but in theory, it's the foundation of this topic. So for example, if you have a mole of atoms, let's say an ideal gas, a mole of argon atoms, you have on the order of 10 to the 23 velocity position pairs. Right, so you have velocity and you have position. Right, these are vectors, and you have they're indexed by atom, and you have 10 to 23 of these pairs. So just an ungodly amount of data. Right, and for those of you who don't know, this script O is often used to indicate on the order of, so other than the order of 10 to the 23 velocity and position pairs. Okay, a macrostate is a description of a system on macroscopic length scale, averaging over microscopic. And by microscopic, I mean that is atomic or molecular processes. So macrostates are what we have been dealing with to date in class. And so we know that even if we might have 10 to the 23 atoms, we can describe the state of the system with a very small number of parameters, like pressure, temperature, and mole number. Right. So at times we can imagine the atoms zooming around. At times we can imagine that, right? And it's you could draw pictures, right? So this is going back to the baby book. This baby book is called Statistical Physics for Babies. So we're back to the baby book, and right, and And so we imagine that we can draw pictures of where the atoms are and how they're moving, right? This is velocity position pairs. But we never actually do it, right? We never really do it. We just, we characterize a system by the pressure and the density and the temperature, a small number of variables. Okay, so we're going to spend some time counting microstates, because it's really through counting microstates that the profound nature of this emerges. Here's a simple example. This is right from De Hoff. So this is combinatorics. Let's say 4 particles, A, B, C, and D, and 2 possible states for each particle. One and 2. And so you can imagine these states are 2 boxes, right? You can imagine a carton that's separated into 2 boxes. We'll call this 1, we'll call this 2, and you can put some particles in here, and you can put some particles in here, and we're going to figure out how to distribute the particles. So, so let's do some counting. Here's state 1, state 2. Okay, so we can have all the particles in state 1. Yeah. We can have 3 particles in state 1. We can have 2 particles in state 1. And I'm going to imagine you could continue filling this in if you wanted to. So these are a list of all possible micro, and you be careful of my writing. This is a list of all possible microstates, right? You can imagine listing these up. So now I'm going to tell you what the macrostates are. Macrostate 1 is going to be something described as follows. All particles in state 1. Macrostate 2 is going to be 3 particles in state 1. All right. Macrostate 3 is going to be 2 particles in state 1. Right, you can continue to delineate these. And now we're now we're going to count. So macrostate 1, that's macrostate 1. So how many different microstates are there within macrostate 1?
Just one.
Just one. That's right. Okay. Macrostate 2 has these microstates. So how many microstates are there that are consistent with this macrostate definition?
4.
4. All right, there are 4 microstates that are consistent with this macrostate. Okay, good. So what we're doing here is we're defining macrostates, and then we're counting microstates. Right? Define macrostates, count microstates. That's what we're doing. So let's do this a little bit more generally. General. Well, before I do the general case, let me again, the baby book is fantastic here, right? The baby book does exactly this. The Hoffman baby book are very similar books. So, right, here's a case of 6 particles and 2 states, and there's only one way for all 6 particles to be all on the left-hand side. So this would be a macrostate called the volume is 1/2. Let's just say this is a volume of 1. This macrostate would be defined as the volume is 1/2. Right? There's only one way for them to all be on the left-hand side. Maybe you say there's 2 ways. The volume is 1/2. It can be left or right. But that's what we're doing. We're counting, right? And then you could say, okay, let's say that I have a state where I have 2 regions, one with density 5 over 1/2 and one with density 1 over 1/2. How many different ways can that macrostate be instantiated by macrostates? You say, okay, 1, 2, 3, 4, 5, 6. There are 6 ways. Right? You could define a different macrostate, right? And you can count. So the baby book here is doing exactly what de Hoff is doing. Right, so now we'll do a little bit more of a general case. Let's do a general case. N particles distributed over R states. N particles distributed over R states. And we're going to introduce capital omega. Capital omega is going to be number of microstates in the macrostate defined as N1 particles in state 1, N2 particles in state 2, and so forth. So the macrostate is defined by a set N sub I. N sub I, that set, describes the macrostate. And sometimes those will be called occupation numbers. So when you do probability and statistics, or when you do quantum mechanics, and especially quantum statistics, you spend a lot of time talking about occupation numbers. So now you've seen that, occupation numbers. I mean, it's encountered in other areas as well. I'm just thinking about, what am I thinking about? I just came out of a talk about material science challenges for quantum computing. And so I was seeing a lot of that stuff. So that's what's on my mind. All right, anyway, here's the answer. The answer is this. And if there's time, we can come back to derive this. The book does not derive this. It's not hard to derive. Okay, so this is the number of microstates for n particles distributed as follows, with n sub 1 in state 1, n sub 2 in state 2, n sub 3 in state 3, and so forth. So again, we can come back to that, but I want to show you something qualitative about that function. For large systems, that is n much greater than 1, and especially when r is much greater than n. So a very, very large number of particles and an even larger number of places to put those particles. This function becomes very sharply peaked. Around a particular macrostate. What does that look like? Here I'm going to plot omega, and it's going to be on a log scale. I'm not going to put tick marks on there, but I just want you to appreciate the orders of magnitude involved. So I'm going to tell you this is a log scale. And the abscissa here are macrostates. Macrostates, let's say indexed somehow. And you're going to have some macrostate for which the distribution of microstates is overwhelmingly higher than for all other macrostates. This area under the curve here. Let's draw that in orange so it's even possible to visualize it. Right. This is a highly peaked distribution function. So again, another concept from probability and statistics. And this state, we will see, is the most probable macrostate. It's the most probable macrostate. So we saw that a little bit, right, at the beginning of class when we looked at ways of distributing 6 balls in 2 halves of a container. And Fenny told us that the reason why this is a more common macrostate, of course he didn't use that term, the reason why this is the most common macrostate is because it has the most number of microstates, right? So this is a macrostate with 1 microstate. This is a macrostate with 6 microstates. This is a macrostate with 15 microstates. And this is a macrostate with 20 microstates. And that was the reason it was the most often seen. You could say it's the most likely. And we will see soon, within a lecture and a half, that it is also the state with the highest entropy. So we're starting to see a connection between equilibrium and likelihood. Okay, so let's do some more counting. So let's work on defining I think I have too many letters in that. Defining, or that is counting the macrostates for n particles in R states. And again, you can think of these as boxes, right? Places to put the particles. All right, so I'm going to do some more counting. I'm going to index these things just so we have an ordinate. And so let's say, and I'm going to write sets of occupation numbers. These are going to define the macrostates. Let's start with all the particles in the first box. So n followed by a bunch of zeros. Right, that is a good macrostate. All the particles, let's say on the left, right? That's what that would correspond to. Let's call that macrostate 1. We could also have all the particles in the second box. Right? Or all the particles in the third box and so on. Okay, then there's, let's see, how many of these states are there going to be? How many of these sort of states are there going to be? These states are defined as all the particles on one box. How many of those are there going to be?
R.
R, right. There are R, choose one of these. I'm using the parentheses notation for the binomial distribution. Some of you have seen this as R, choose one. It's a little more compact to write in parentheses. If you've never seen the binomial distribution, we should make time to talk about it. But why is it R choose one? It's because you have R states and you're just choosing one of those states into which you're going to put all the particles. Right? So R choose one. And by the way, R choose one is just R. Right? You have R choices. Okay. All right. Next. What about states that are where you have n minus 1 particles in a box and 1 particle in another box? And the other box is, of course, empty. And then there's going to be a bunch of ways that you can do this, right? Here I put n minus 1 particles in the first box and the remaining particle in the second box. Here I put n minus 1 particles in the first box and the remaining particle in the third box, and so forth. Okay, this is a challenge. Can somebody tell me how, in a compact way, to count how many of states such as these are there? How many total macrostates such as these are there? How do we think about it? I have R boxes, and out of those R boxes, I'm picking 2 of them. I'm choosing 2 of them. I'm choosing 2 of those boxes to have particles in them, where the rest are empty. So do we have an expression for how many ways can we choose 2 boxes out of R boxes?
R choose 2.
R choose 2. Good. And this keeps going until you get to R choose minimum of R and N.
Can I ask a question?
Mhm.
Would it be R choose 2 regardless of how you distribute the particles within those two boxes? So like say you did like n minus 2 and then 2 in the next, would it still be R choose 2?
N minus 2 and then 2. That
Or
would
oh,
be
okay, like
art.
by definition you can only have like max 1
No,
or
that's okay. That's going to be a
okay.
different set, and that would also be counted this way. It's just not the
Okay.
way that I've defined it here. No
Okay.
problem. Yeah. I mean, there are so many ways of doing this. I'm only sort of giving you a very introductory example here to how to start thinking through it. But you know, we'd be writing all day if we were to write these all out, right? We'd be writing these all day. But that's a good way to think about it. So, okay, now in principle, we now know how to identify, or I could say count, the macrostates. Right, we know sort of a systematic way now to generate these sets. And the resultant of Hoff, we know how to count microstates for each macrostate. Right, we have kind of a systematic way of moving through all the macrostates and describing them and counting them. And we have an equation for the number of microstates for a given macrostate. So we have this procedure, we have this algorithm, and so now we can calculate and plot the distribution function or log sigma or omega. So let me show very, very simple case, extremely simple. So I wrote a little script that does this, and I ran the script for a couple cases. And so as I move from left to right here, I'm changing R. I have 3 particles in 5 boxes, 3 particles in 10 boxes, 3 particles in 20 boxes, and 3 particles in 100 boxes. The top and bottom plots are the exact same data set. I'm just distributing them differently. It's the exact same data set. Distributions visualized with different sorting. And so with 3 particles in 5 boxes, the log of the number of microstates spends some time around 0. That's 1, right? Log of 0 is 1. So that these are conditions for which there's 1 microstate. And then it jumps up and it spends some time around 1 point something, and then it jumps up and it spends some time around 2 point something. And what I want you to see is as the number of boxes gets higher, the distribution of microstate count gets more sharply spiked. So what you're seeing is even at low numbers, 3 particles in 100 boxes, you're entering a situation where this distribution function is becoming very sharply spiked. And this is a very small number case, right? 3 particles in 100 boxes. I tried to run 10 particles in 100 boxes, and I calculated that on my computer it would take about a year. So these numbers get really big really fast. If you typed in Avogadro's number here, I think your computer would literally laugh at you. Right. But you're supposed to see qualitatively that this function is becoming sharply spiked. that has profound implications, right? That's why I'm spending time on it. So why does that matter? Why does it matter that that distribution is sharply spiked? Who cares? It cares because of something called the ergodic principle. I'd never heard that word before I took statistical thermodynamics or StatMax for the first time. So maybe you have, I don't know, maybe you're more well-read than I was. But I've never seen that word outside of this context. It's like the weirdest word. Where does it come from? I don't know. If anyone knows where it comes from, I'd be curious. Anyway, this is what it is. The ergodic principle is the following. It's a hypothesis. It's not always true. Here's the hypothesis. All microstates that are compatible with constraints are equally likely. That's the ergodic principle. So we have a word here, which is, again, from another discipline. We have the concept of constraints, which we're familiar with, but, you know, here it is again. And we have this sort of funny new word. So this gives rise to the concept of ensembles. Ensembles of microstates. I'm going to use shorthand here. Ensembles of microstates that all satisfy given constraints. So what's an ensemble? An ensemble is a collection, right? So here's an ensemble, right? Here is the ensemble of microstates that all satisfy the constraint that the volume is the full rectangle with solid lines, right? That's the constraint. The constraint is that the volume is the full volume, and this is an ensemble. It's an ensemble of different microstates that all satisfy some clearly stated constraints. And here is something a little bit profound. A corollary of this is that time averaging is the same thing as ensemble averaging. Time averaging is the same thing as ensemble averaging. And for those of you who like probability and statistics, this connection between time averaging and likelihood is known as frequentist probability, as opposed to Bayesian. Right? So what does that mean? The time average is the same as the ensemble average. It means that if you can write down the ensemble of all possible microstates that satisfy a given macrostate, if you can write down the ensemble of all microstates and you average over that ensemble, the average you get for any observable quantity, be it pressure or temperature or magnetization or density or what have you, that average is the same as if you take a given system and evolve it forward in time and take a time average. So, in other words, like this. The average you get when you average over this ensemble is the same as you would get if you start with just that and then play forwards in time and average over the movie. That's what time averaging equals ensemble averaging means. And the likelihood of finding a given macrostate is proportional to its number of microstates. The likelihood of finding a given macrostate is proportional to its number of microstates. The probability of finding macrostate J is equal to the microstate number for macrostate J divided by the microstate number summed over all macrostates. There's number of microstates in state J. So that is, this is total number of microstates within constraints. And this is the probability of finding macrostate J. So that is. So let's go back to the baby book and to the plots. So if we have constraints that the particles just have to be somewhere inside of this gray box, or we have 1 microstate here, we have 6 microstates here, we have 15 microstates here, and we have 20 microstates here. And then we're going to have another 15 with the particles weighted more to the right, another 6 with the particles weighted more to the right, and another 1 with the particles fully on the right. So we have, say, 1 plus 6, that's 7, plus 15, that's 22. 22 times 2 is going to be 44, and then 20 is going to be 64. So we have 64 total microstates. And the most likely scenario is this one. Why is it the most likely scenario? Because its likelihood is 20 divided by 64, right? You have a 20 over 64th chance of finding something that looks like this. You have a 15 over 64th chance of finding something that looks like this. You have a 6 over 64th chance of finding something that looks like this. And you have 1 over 64th chance of finding all the balls on the left, right? So the balls do not know what they are doing, right? They do not care about any of this. They move at random. But somehow from their collective behavior, some simple rules emerge that you're far more likely to find this scenario. And 20 over 64 is not a very large number, right? That's only because we're dealing with 6 balls in 2 compartments. 20 over 64 is not that large of a number. But when you have a distribution function which looks like this, where this is now log of microstates and this is number of macrostates, you can see that this number, right, taking the exponent divided by this number is very, very large. That's the likelihood that you're going to find this macrostate instead of this macrostate. And I think in very first lecture, I referred to this as being, the reason why we don't have to worry about suddenly suffocating, because all of the oxygen molecules in the room have decided to go into one corner, right? The oxygen molecules move at random. Perhaps if you waited a very long time, you would find a snapshot in time for which all the oxygen molecules were in one corner, but none of us expect to find that. Right? Why is that? Because the likelihood of them being evenly distributed through the room is overwhelmingly close to 1. Okay. So that is all following from the ergodic principle. right? All microstates that are compatible with constraints are equally likely. So likelihood follows microstate counting. All right, so that's all I wanted to get through today. I want to leave you with a question, which is something we can discuss, and it gets to the P set. For what types of systems might the ergodic principle break down? For what types of system might this break down? So we had this example that ensemble averaging equals time averaging. And I said, what is a time average? Well, let's take a snapshot and time equals 0, call it. And we'll play the movie forward. And we'll average over the time history of that movie. That implies something. What does that imply about this system?
Maybe that it's closed and there are no additional particles being added.
Good. That's good. That's not what I was going for. You're talking about the boundary conditions and constraints. There's something else, though, that is beyond the scope of this class. It's the title of a course you'll take in the fall. What does that imply about the system?
The kinetic energy is constant, maybe?
Kinetics. It's not quite what you said, but you said the key word, which is kinetics. It implies that kinetics are sufficiently fast that the movie will play. So if you're at 0 Kelvin and nothing is moving, if this is your starting point, this is pretty much where you will remain. So your time average will no longer be your ensemble average because the particles don't move anywhere, right? So you only get this sort of sequence of snapshots in time if the particles are moving at all. So systems that have sluggish kinetics violate the ergodic principle. What's something that we said about equilibrium way at the beginning? Equilibrium is a state of rest. Equilibrium is what you get when you wait long enough. And we've never quantified long enough, right? We don't really do that in O2O because this is a course on equilibrium thermodynamics. We don't quantify long enough. But the idea that you have to wait long enough for a system to evolve to equilibrium is equivalent to the concept that you have to wait long enough for the time average to become the ensemble average for any of this statistical thermodynamic stuff to work. Those turn out to be quantitatively the same thing. Okay, so we talk about kinetically sluggish systems. Kinetically sluggish systems, systems that don't move very fast. They don't move fast enough to reach equilibrium. That might be an example of the types of systems for which the ergodic principle breaks down. Okay, I have 4 more minutes, and one thing which I could do with those 4 minutes is go back and show you how this comes about, because this is just stated in the text without proof. But I could also answer questions about this or anything else. So let's start with questions about this material or even the material that we finished with Professor Olson's lecture, or the problem set, which is due today. There's another problem set that goes out. Oh, I'll mention. The problem set that goes out today is P set 9. It's due Thursday because Friday is a student holiday. And it is shorter than I would otherwise give you because you have one less day to work on. So don't forget that. Any other questions on any of this?
Could you go back to the counting macrostates page?
Sure. Sure.
Yeah, this one. So for that one where you have R choose 2, so are you like, will the n-1 always come before the 1? Because like first you choose like which 2 boxes will be occupied, right? So there's R choose 2 ways to do that. But then don't you also have to choose like which one has n-1 and which one has 1?
Yeah. You do. So that's another case of it that I don't draw out here.
Oh,
I
okay.
thank you for that. So if you like, so here, right, Baba, I'm not being explicit here. I'm writing sort of suggestive cases and then putting ellipses, dots, right? So it's like, what on earth is he talking about? You're getting to an ambiguity in the way I've written this out. So it's the same ambiguity that you have here. Does this picture stand for one state or does this picture stand for two states? It depends how you count, right? If I imagine that, Chris Ferry, he's a research physicist. He actually works in a quantum computing center in Australia. This is to say that he's a smart person, and I gather that he could do this accurately if he chose to. But this is the baby book, right? So he wasn't explicit about, oh, there's actually two states and they're equivalent, right? Does that make it? Are you following me here with respect to
Yeah, so
baby book?
basically
Right.
what you're saying is like if you were to write out, you would also have one where it would be like 1, n minus 1,
Right,
and that would be like
right.
counted separately.
Let's flip
Okay.
that. So if you want to say that we're counting those, we just double it
Okay, that makes sense.
in this case. But then the next case down, you can't just times two it. It becomes more complicated. So, accounting is not easy sometimes, right? And so you can imagine that if I asked you to sit down and do this bookkeeping correctly, you could. And don't worry, this is not a case that's on the problem set. But you could do it, and other people have done it, right? I tried to do it in a MATLAB script that I wrote to produce those plots, for instance. So, yeah, good point. Good point. It all comes down to sort of how you think about doing combinatorics.
My question was basically equivalent to, so I'm glad that you asked it. Thank you. But then for like the slide before that then, or maybe it was like 2 slides before where you're just like counting states in the very beginning. When you were doing like 2 particles in state 1 and 2 particles in state 2, like just like you explained it here, that would mean that like if you had say like AB state 1 and CD state 2, that would count separately than AB state 2 and CD state 1, right? Like those would be 2 different cases.
Yes. Yeah. Again, another case where I just put ellipses and I wasn't explicit.
Okay.
Yeah.
Okay, so like the type, basically like the type of particle matters. Like we're labeling these particles. It's not
We're
just
labeling these particles. We're labeling
Yeah.
these particles. Yes, we're labeling
Okay.
these particles.
On the R choose 2 on that like slide, could you talk a little bit more about how you draw that conclusion? I'm not super familiar with like the way that you wrote it out.
Sure. So let me finish this comment on labeling these particles. This is all classical statistics. It's perfectly fine. It gets you a long way. When you get to quantum statistics, you have to start dealing with indistinguishability. And you have to, well, this might be much more than you want to know at the moment, but I'll share it because I think it's kind of cool. Imagine that all of these grid squares are states, and I have 2 particles, and let's say they're the same isotope of an atom in the same spin state, same quantum numbers. In that case, they're indistinguishable quantum mechanically. So I want the modulus squared of my system wave function to be unchanged if I exchange these particles, because they're indistinguishable. That still gives me a choice of sign in the wave function, because a negative number squared gives you a positive number, and a positive number squared gives you the same positive number. And that's the difference between bosons and fermions. And it produces very, very different physical behavior, those statistics, quantum statistics. And actually, there's a quantum computing scheme that uses anyons, where the phase is imaginary. And anyway, so you're getting somewhere which we don't have time for in this class. But right, okay, so that was a point on distinguishability versus indistinguishability. The other question was about combinatorics. So here, I have R states, right? And 2 of them are special. Two of them are special because they have some particles in them, right? And one of them I've put n-1 particles and the other I've put 1 particle, and all the other states are zeros. So one way to think about defining such states is I'm just picking 2 boxes out of all these boxes. Right? So imagine again, the grid square here are all the possible boxes, and I just have to pick 2. I just have to pick 2. So the combinatorical expression R choose 2 does that for me. I'm picking 2. All the rest are 0. So that's sort of funny. You think about have to write all these zeros down. Forget about writing all these zeros down. Just choose 2 that have some particles in them. And by the way, R choose 2 times 2 is R pick 2, right? So that's the difference between a pick distribution and a choose distribution. But anyway, right? So let's say I have 3 boxes with particles in them. Well, I didn't even draw that case, right? Then it's R choose 3. You choose 3 boxes that have particles, and all the rest you forget about. Right? And in general, right, A choose B, which is the same thing as sometimes it's written this way. A choose B is what? It's A factorial over B factorial A minus B factorial. So anyway, if this is unfamiliar to you, the wiki entry is a good place to start. I mean, if you haven't seen this before. I hope that helps.